we start today on page 12, but first a look at the calendar. I know a bunch of us are working on the projects. If you have not started working on the project, it is time. Begin to work on the project. I've already got somebody who's turned the project in, and I'll give it back, and then you'll have a week to revise. And you can turn it in anytime, including the day of the final exam, but you got to make sure you give it to me early enough if you want a chance to do a revision and change that grade. I've highlighted 3 days here. These are the last 3 classes, including today. And the common theme in all of these days is math in nature. And so we spent a day talking about the Fibonacci numbers and the bees. And last class we talked about population growth, like the rabbit example. And today we talk about this crazy thing called a fractal, which hopefully you did some reading about. Also want to point out that at the end of today, we will be halfway through the material for the last test. The last test is only on 6 days of stuff. Today is day number 3. Questions on the calendar? Okay. Then let's have a look at page 12. And can we go to Blake all the way at the bottom, number 1? Thank you. Jocelyn, number 2. Page 13. And number 2. We'll start. Okay, so here's our first example of something called a fractal. The word recursive is here, so we're going to be doing something over and over again. So you start with an equilateral triangle, and that is called the seed, the starting point. And then what we're going to do is a process. We're going to take each of the sides of this equilateral triangle, and we're going to add an equilateral triangle on top of it. What you're going to do is you're going to break this triangle up into thirds. Like each of these sides can be broken up into 3 pieces, equal pieces. And you're going to take one of those sides, and you're going to draw a little tiny equilateral triangle sticking out right in the middle of that side. And you're going to do that same thing on every side. So we end up adding 3 new, tinier equilateral triangles. You with me so far? If the original side right here, let's just make up a number, suppose that that thing is 18, then how long are the purple line segments? I heard one answer. Can I hear more? How long are those purple line segments if the whole side is 18? I heard the same answer from the same person. Can I get more people? A few people, we see 6. It is 6 because you're taking 18 and cutting it into 3 parts. So that's a 6, that's a 6, that's a 6. Which means that this little triangle here has sides of length 6. And so we take them and we stick them on and we get this guy over here. Questions on step 1? Okay, step 2, same as step 1. You take each of the sides of this new shape, the star shape, and you cut it. Here's one example of a side of the star shape. I cut it into 3 pieces, just like I did before, and in the middle, I'm going to stick on a little tiny equilateral triangle. And on this side, a little tiny equilateral triangle. And on this side, tiny equilateral triangle. And in the middle of each of the sides, a tiny equilateral triangle. You guys already told me how long this blue one is. How long is it? It is 6, right? We saw that before. Can you guys hold up the number of fingers that is the length of the sides of the small little equilateral triangle over here? How long is each of those sides? Good. So lots of 2s because you have 6 cutting into 3 pieces. Each of those are 2s. Good? Okay. And so we can continue this process for a while. After you do that, the next step, step 2, you end up with this shape over here. So a star with lots of points on it now. And you can repeat. And I'm just going to draw 1. But like on every little side of this triangle, what are we going to draw? little tiny equilateral triangle on every side of that star-shaped thing. And so if we look down here, you'll actually see several iterations. The seed is just a basic triangle. Step 1 was our star-shaped thing. Then it becomes a little bit more star-shaped with more points in step 2, and step 3, and step 4. And the reason I stop at step 4, you could go forever, right? You could just keep doing this. But what would step 5 look like? It's going to look to us the same as step 4, unless you have like a magnifying glass and really, really good resolution on the thing you're looking at. The triangles now are so tiny that I'm not even going to know that they're there. I just can't see them. But you could go forever, in theory. Okay, let's go to Justin for E. Okay, thank you. Hillary, number 4. Yes. Okay, so this Koch snowflake, in theory, is the thing you get if you carry this on forever. The true Koch snowflake looks an awful lot like the thing in step 4, but it goes forever, okay? And so it's just this idea. You can think about it, but I can't tell the difference between step 4 and 5 because they look the same to the naked eye. Okay, let's go to the next page. Number 5, Zach. Okay, so going back to our original picture with all of the steps laid out for us, if it originally starts with a 27, how long is each side if perimeter is 27? These are each 9s, right? And now the perimeter here, is it more or less than the 27 that we started with? It's more. Do you see that it's more? Maybe it's not clear that it's more, but we did lose some stuff. Do you guys see that, like this part right here, that used to be part of the perimeter? It's not there. It's not part of the perimeter anymore, right? So we did lose some stuff, but we replaced it. We replaced that red thing with these 2 green things. Which one do you think is more? I say green, I meant purple. So which one do you think is more, the one red or the 2 purples? The 2 purples are definitely more than the one red. So the perimeter has gotten bigger. The perimeter here was a 27. I don't know what it is here. Maybe 40. Who knows? How about on the next one? Is it going to be more or less or the same? It's going to be bigger. Now, I've made it so that we gained 13. I just made up a number. Maybe it's bigger by the same amount. Maybe it's bigger, but not by as much. Maybe it's bigger by even more than the first one was bigger. There's a lot of possibilities here. Could you guys make a guess? If we go to step 4, step 5, and then forever, the perimeter of the forever one, the last one, 60, 100, 1,000,000, infinite? Just make a guess. Just write down a guess based on hardly any information. If you go forever, is it something like 50? Is it something like 100? Something like 1,000,000? Is it infinity? We'll answer that question later. You should have no idea, but you could at least guess. We'll come back to that. Let's go to Ashley for 6. 6. Okay, so again, going back to the seed, instead of thinking about perimeters like we did before, what are we thinking about now? We're thinking about areas. So we scratch all this stuff. Think about areas. And we said the area was originally, what was it? 35. So there's 35 square units of space inside of that triangle. Does the next triangle or the next star, does it have more or less or the same area as 35? It's more. It's clearly bigger. Okay, I'll make up a number. 42. I don't know. The next one, does it have more or less or the same as 42? More. Okay, I don't know. 48. Just making stuff up. If I go forever, every time we get more, same question as before, which you still should have no idea how to answer. But now for perimeter, now for area. If you go forever, what do you think the area of that infinite one is going to be? Do you think it's going to be 50? Do you think it's going to be 100? Will it get to 1,000,000? Johannes? Will it be infinite? Yes.
I feel like after a while,
so the change won't matter. So Wadada is saying even though it gets bigger and bigger, maybe it'll still level off somewhere, some finite number. Jason?
Yeah, piggybacking on that, because your perimeter may continue to increase, but you're not actually going to be taking up much more space. Like at first, you'll see like a significant difference in area, but after a while, when you're dealing with microscopic triangles, change in area is going to be fine.
Okay, so we're adding tiny, tiny, tiny little triangles. So maybe the area that we're adding is just insignificant. But then the same kind of question comes back to the perimeter. We're also adding tiny, tiny perimeters. So is that change significant or is it insignificant when we get far enough down? We're going to answer both of those questions by the end of today. Okay, let's move on to Johannes for...
Similar, but even smaller part, so on. In other words, when we zoom in on a small piece of the edge of the snowflake, it just looks like what we're looking at to begin with.
Okay, so this is quite strange, but it's true. If you draw this Koch snowflake out for a long time, you eventually get some shape like we've got over here. And then you could maybe focus in on one little part, one little corner of this snowflake. And so I'm going to blow up that corner. You guys see the blow up inside of here? That little corner is now blown up. But what does it look like? Looks like the whole thing that we started with. And then suppose we have lots of magnitude or what is it called? Magnification, thank you. Lots of magnification and enough detail that we can actually see what's happening. So we're gonna blow up this tiny little thing here. And by the way, that tiny little thing there is probably only just like it's from the point. Like it looks like a point to us, but we blew it up and it actually turned out to have some more space. And then we blow that thing up. And what does this look like? The same as the original. And it's very strange. But if you keep zooming in, it keeps repeating itself. There's no end. It'll go forever, and it'll always look exactly like it looks in the first spot. Okay, there are some really nice videos on YouTube. We're going to watch a 30-second one. 8 for Kelly. Okay, so that means that it goes forever and it's always the same, universal. It always looks the same at every spot and it's exact, meaning it's perfectly similar to itself every moment of the trip. Iris for number 9. Okay, so we're playing with triangles and it's just this like mathematical idea that somebody decided to play with. But what does it have to do with real life outside of a math class? Well, there are a lot of places that have this kind of property where if you keep zooming in, it looks exactly the same as when you were zoomed out. And so here are a few examples. What is this first thing on the left? That is a fern. And everybody can look at that and know that it's a fern. Suppose I didn't show you the whole picture, but rather I just showed you this piece of the picture. You didn't see everything else. What would you call that thing? You'd say, oh, look, it's a fern. And instead of that, suppose that I were to just show you this piece right here, but I'll blow it up for you. I'll make it a lot bigger. What would you call it? It would look like a fern. I mean, like at some point it will end. At some point it stops, right? It doesn't go forever. But we could kind of go for a little while looking at little pieces of ferns, and what do they look like? They look like entire ferns. Same kind of thing is true about this crazy shape in the middle here, this green thing. Has anybody ever seen that thing before? Yeah, it's a vegetable actually. It is called the Natalino Romanesco. It is edible. It tastes like some combination of cauliflower and broccoli. Really wild, but there it is. And if you zoom in, what does it look like? Looks like spirals. And doesn't it look like the original thing? Like if I were just to focus in on, say, this top branch right here, maybe it looks like this new picture. And that new picture has a branch that I could focus in on. And if I focused in there, it would look like the original vegetable. It always looks the same for a little while anyway. Okay, down here, anybody know that picture on the bottom left? That is a fiddlehead fern, another vegetable. If you zoom in on part of the fiddlehead fern, what does that look like? A fiddlehead fern. How about the next one? Yeah, so I don't know if that's like a coastline or if it's like a frozen type thing, like in the Arctic. But if you zoom in on that, what will it look like? The coastline. It won't look like a part of anything. Like this could be, it could be zoomed out, or we could be like sitting right there, like on the beach, looking at the water coming in, and it looks kind of similar to how it looked from far away. And then finally, the last one, what is it? Lightning bolt. What if I didn't show you the whole thing, but just showed you that? What would you say? Oh, that's a picture of a lightning bolt. And if I just showed you this piece, real bright, oh, look, that's a full lightning bolt. Okay, so this idea, maybe it's just this math thing that we're doing where we play with triangles and perimeters and areas, but the concepts kind of show up pretty often, actually. Next page. And we're going to play around with this activity, which will take us quite a bit of time. So we're going to create the Koch snowflake from scratch. You guys are going to do some drawing of stuff. And what I'd like you to do is we'll start filling this thing in together at the beginning, and then you guys will work in your groups. So part A, can we go to Brittany? Okay, on the next page is some graph paper. It looks different from any graph paper you've ever seen. What's the fundamental shape for all the graph paper you've ever seen? Squares. These are triangles. It's easy to draw triangular stuff on triangular graph paper. So what you're going to do is go somewhere in the middle of this thing, and you're going to draw your seed triangle. If you happen to have a straight edge, then you should use it, maybe another piece of paper or your calculator or your book. Somebody can use the folder. You're going to draw something where it's an equilateral triangle with 9 units on every side. So 1, 2, 3, 4, 5, 6, 7, 8, and I think one more makes 9. So you want to count 9, used to be squares, now it's 9 triangles. Just try to put it somewhere in the middle. Doesn't have to be perfect. And once you've got that one side with 9 things on the side, you don't need to put the 9 on it. And you draw the other 2 sides. Make your full equilateral triangle. When you've done with that, go back to the previous page and follow all the directions on that page. There's a lot of stuff to do. See if you can work with your neighbors. All right, so come on back together. What was the pattern in the first column? What happened to get the next number in the first column? Always times 4. That's what it turned out to be. Turns out there's a pretty good reason for that. Maybe it wasn't clear. It probably should not have been clear that it was going to be a times 4 every time in terms of the number of sides. But take a look. Look at this one side here. It is currently one side in the calculation, and then it gets replaced with how many sides there? That's 4 sides. One side became 4 sides. Is that true every time? Let's take a look at this piece right here. It used to be one side. Then it becomes this, 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 this. How many sides? 4. So every single side becomes 4 sides. So maybe that timesing by 4 makes sense because everyone gets replaced with 4 sides. So times 4. So I've got that pattern written down. here, just in English, multiply by 4. How about the middle column? What was the pattern there? It's divide by 3, which makes sense because you're just cutting into a third every time. Instead of saying divide by 3, I wrote multiply by 1/3. We believe that's the same. Dividing by 3, multiplying by 1/3.
If you divide a third by a third, you get more than what you had before.
Yeah, if you
Start going backwards here.
Okay, and then the perimeter. Let's see if we can come up with a fancy way to find the formula or a pattern here in the perimeters. To get the perimeter, what we did every time was multiply the first 2 columns, right? That's how you guys found the perimeter. Okay, well, let's think about it. The first column is getting multiplied by 4. The second column is getting multiplied by 1/3. So then when I multiply those multiples, these guys are going to get multiplied by 4 and then multiplied by 1/3, which is really the same as what fraction? 4/3. There's a pattern in that last column. Not as easy to find as the other ones, but every time it's multiplied by 4/3 times 4 because of the first column, and then divide by 3, you can see in the second column. So let's look at it. If I take my calculator out, so probably we didn't do it this way, but here's a real nice way to just get the last column. If I start by 27, and what am I saying I multiply by to get the next number? 4/3 every time. 4 divided by 3. Is it 36? Yes. How do I get the next number? Multiply that thing by 4/3 times 4/3. Is it 48? Yeah. And the next number, I'll just hit enter because it's timesing by 4/3. Is that the next number? Yeah, so this is kind of a really nice way to think about finding the column. And in fact, it's easier to hit enter here a bunch of times than it was to actually do the calculations. What does it appear is happening to the perimeter of the Koch snowflake as you go forever? Increasing. Increasing and maybe leveling off, or increasing without bound. It sure feels like this is increasing without bound. After however many times I hit enter, the perimeter is now over 1 million. That is to say, if you were standing here on maybe not step 4 of the Koch snowflake, but maybe step 20, I don't know how many times I hit enter, and you decided you wanted to walk around this whole thing, well, it doesn't look very big, and maybe it's not in terms of the area, but how far would you have to walk? 1 million feet to get all the way around. If this is originally a 1 foot on the side, 1 million feet walks all the way around. And if I go another one, and it's like, 2 million feet. So it feels like the perimeter is getting bigger and bigger and bigger without bound. All right. Now we're going to tie this stuff into what we did last class. Do you guys remember that we had a couple of formulas last class? We had linear growth and we had exponential growth. Linear growth says you do what over and over again? You add the same thing. For linear growth, you add or subtract the same thing. Like we had that nuclear waste example where every year we had 5 tons more. That's linear. Is that what you're doing in any of these columns? Are we adding the same number over and over again in a column? No. What are we doing instead of adding? Multiplying. Multiplying by the same number is a different name. It's not linear. What is it? It's exponential. We had 2 things. We had linear, we had exponential. When you multiply by the same thing, that's exponential. Same with division. Multiply or divide by the same thing. So what I'm going to do is remind us of the exponential formulas that we saw last time. You probably used these formulas in your homework last night. So there were 2 versions. There was the recursive one, where you said, okay, if I want to know the current number, I take last year's number and I multiply it by the right thing. Multiply by whatever we're multiplying by. That's the recursive version, where you just keep saying continue to multiply over and over and over again. The explicit version, which turns out to be a whole lot more useful if you can get your hands on it, is this. It's the start amount times that common ratio raised to the n. So let's see if we can figure out specifically for these examples, those columns that we just had, what the formulas should be. Okay, first thing. I've got 3 different columns. I'm going to name these things with 3 different letters. The number of sides, I'm going to call that S. Instead of P, which is what we used all last class, P for population, I'm going to do S for number of sides. I'm going to call these guys the L's for the lengths. And then over here, we're going to call it P for perimeter. Okay? S, number of sides, L, length, P is perimeter. Okay, so just to be clear, this number right here is what I'm calling S0. That's the seed starting number. That's S1, the number of sides 1 generation in. That right there is S2, number of sides 2 generations in. So it's the same as we had before. I'm just using S instead of P. A list of numbers, a little subscript tells you what generation you're at. What's a good name for this 9 right here? What letter are we using there? That's an L, and it's the 0 piece, the starting piece, the seed. What's a good name for the next one? That's L1. That's L2. And the list goes on. We're just giving names to this list. Finally, in the perimeter column, what's a good name for that 27? That's P0. And then P1 and P2. Perimeter in the second generation, second step. So it's all well and good to list these specific 9 numbers, that's fine. But what I'd really like to do is make a leap between the specific numbers and the more general formulas. That's what we want to use. If I want to know what's happening in the 50th generation, I'd really prefer not to have to do something 50 times to get it. I don't want to have to fill in 50 rows to get to the one that I actually want. I'd really much prefer to use a formula. So let's see if we can piece our way through these formulas. Okay, we will start with the sides. What letter were we using for the sides? Number of sides was S. Okay, so we're using this first blue formula, the recursive one. Used to be Pn, now it's just Sn equals Sn minus 1 from the, used to be P, now it's S. And the only thing you really have to do here, the only work, is to replace the R with the magic multiplier. What did you multiply by in that first column every time? It was times 4. That's your recursive formula. That's the math way to say times by 4 every time. Question? Jocelyn? We're going to do that in the second version of the thing. Right now, that's just the recursive. We're going to write the explicit, which is what you're quoting right now. The last time, I don't think I did a good enough job of making really clear what this whole n business is. We have specific numbers sitting way up here. It's fine, but I want to talk about general. I don't want to talk about S2 or S3 or S5. I want to talk about some arbitrary, some generic S row. And so we're going to call it Sn. And to me, Sn is just the current number of sides. I don't know what generation you're on, but let's just call it the now, the current. And how do you figure out how many sides you should have now? Well, you take a look at the number of sides you had last generation, 1 generation before now. That's the minus 1. So the n is now. It even starts with the letter n. N minus 1, 1 year before, right now. How do you find the number of sides? You take last number of sides, multiply by 4. That's all it says. From what I could see in last class, some folks wanted to take this formula right here, and they were trying to find a number to replace this p of n minus 1 with. Try to find something in the problem that you're supposed to stick there. You don't. It's just part of the formula. How many sides do you have now? I don't know. Find last year's number, last generation's number, multiply by 4. That's the formula. There's nothing else to replace there. Let's go to Jocelyn's version, which is the more useful version. It's now this second formula. Okay, it's not Pn. Which one? I'll write it down. We have this one is the recursive, and this one is the explicit. Two different versions. So let's get the explicit one. Okay, so this one says, all right, it's not P. What letter are we using for this one? S. S, N equals. What was the starting number of sides? It's in the table at the top. It's 3 times the ratio, the magic multiplier. What's the multiplier in that first column? 4. What's N? It's N. Stays there. It's the number of steps you're going to make. Jocelyn, is that what you had said? Jocelyn, this is what you said? Yeah. So let's make sure. All right, so do we see where the pieces go? How they get replaced by the numbers? Yeah. So the idea here is that we're going to go with this version, the explicit version of the formula. It says you take your starting amount. What was the starting number of sides? It was 3. In the parentheses, you put the ratio. That is the number that you multiply by every time. In that first column, what did we always multiply by? Was 4. Every time in the first column we multiplied by 4, that's the 4. And just gets copied. Well, I want to see this formula in action. Let's write down S2. According to the formula, what is going to become 2? It's the n. All we're doing is changing the n's to 2's. So this is 3 times 4 to the 2. 3 times 16 is 48. Does that number sound familiar? Wasn't that what we had for the number of sides in the second generation? Yes. But the beauty of this formula is that you could find the number of sides in the 20th generation without any more work. Just change the 2's to 20's. Calculator can handle it, right? You don't have to fill in 19 rows to get this number. If you want S20, what do we put? It's that black formula. 3 times 4 to the 20. That is what we put. All right, it's some massive number. Can somebody type that in for me? What is it? 0.099511628. What'd you get? 3.29? Can somebody else confirm one of these numbers? Second one. Seconded. All right. Second one. So what does it mean? It means that if you go 20 generations into this process, you guys maybe went 3 or 4 when you drew it. If you draw 20 generations, then this is the number of sides. That enormous number is how many sides you will have on this shape. 10 to the 12th? Is that millions? What is that? Billions? It's trillions. There are about 3 trillion sides when you go 20 iterations into this thing. Linda. Mm-hmm.
I use the recursive if I have generation before. If I don't have to generate before, then I go to.
It depends on what you're asked. On the test, I'm probably going to say write down a recursive one, and then separately write down an explicit one. I might just ask you for both. It's really not a matter, like with the information we have, you can write down either, you can write down both. It's generally not going to be a matter of like choosing one or the other based on the setup. With this information, I mean,
I only have up to generation 4.
Right.
I don't have generation 19.
That's right. So if you want to find 20, You either fill in the rest of that table with the first 19 rows if you want to use the recursive version, or probably better is to use this guy. So, I mean, any calculations we do, we're always going to grab the explicit because it doesn't rely on the first 19 rows. Yeah, good question. Okay, so we've got our two versions here. Can you guys in your groups write down the same kind of formulas, but for the length of each side and then for the perimeter? I'm looking for 4 more formulas. 2 formulas for the lengths, 2 formulas for the perimeters. All right, come on back. Let's first focus on the length. Here's the formula for the recursive version of anything. It's the current number is equal to the last number times the magic multiplier, the ratio. For the length column, what did we keep multiplying by every time? It was 1/3. You could put divide by 3. I'm going to always do a multiply. And in this case, it's a multiply by 1/3. That's it. That's the formula. Again, translating this from away from the symbols, but more to English. If you want to know what the length is of each side in the current generation, you'll look at the generation 1 step before, you multiply by 1/3. That is, multiply by 1/3 every step in that column. More useful is the explicit. The explicit says you need to find the starting number and you need to put the common ratio in the parentheses. For the length, what was the starting number? It was a 9, right? The original triangle had a 9 in this problem. Inside the parentheses goes the magic ratio, the multiple. What did we multiply by every time in this column? 1/3. That right there is the formula for the explicit version. Yes, that's why we need the parentheses. Okay, so we've got our 2 versions for the length. We play the same game with perimeter.
First one is recursive, the second one is exponential.
Correct. Okay, perimeter. Same idea as before. To find the current perimeter, you take last year's perimeter and multiply it by the magic number. What is the magic number for that last column? It was 4/3. That's what we discovered. The last column kept multiplying by 4/3 every time. Okay, now we do the explicit one. In the first space goes the starting amount. What was the starting perimeter? It's 27. In the parentheses goes the multiplier, the ratio. What was it for the perimeter column? It's 4/3. That right there is your formula. If, for example, you want to find the perimeter at stage 3, what am I putting for these ends? Putting a 3. So on my calculator, I can type in pretty quickly. 27 times 4/3 to the 3. That right there should be the perimeter in that stage 3. 64 is what you guys have in your table, right? You had to do a bunch of work to get that 64. You had to fill in everything else above. But if we have this formula, it zips it to you. And I can do the same thing and jump down to the 5. Anybody have this number in the table? What's the perimeter at stage 5? $113 and change. Wonderful. So it's a whole lot less work to do this than to fill in everything else above that row 5 to get there. And now maybe we can understand why this perimeter is getting bigger and bigger. Every time, what do you do to the perimeter to get the next perimeter? Multiply by 4/3. What happens to a number when you multiply it by 4/3? Does it get bigger or smaller? It gets bigger. You're multiplying by something more than 1, right? You're not doubling it, but you're still multiplying it by something more than 1. In fact, 4/3 is 1.3 repeating, 133%. So whatever the number used to be, it becomes 133%. It's bigger. So the more times you go, the bigger the perimeter will get. Walking around that Koch snowflake could be millions of miles, even though I could picture it right here on this little screen, right? 6 feet by 4 feet. I can draw something that has a perimeter of 1,000,000 miles in it because of all these little tiny, 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 like molecular sized side lengths.
So it won't out that.
It never levels off. Every time it's 4/3 as big. Okay, so the perimeter gets really, really big. And the other question we were interested in talking about was the area. So let's think about areas. Okay, down here at the bottom of page 17. On page 17, there's a formula that that probably very few of you know, and maybe nobody's even seen it before. What's the standard formula for a triangle? Like if you have a base and you have a height. What is it, Zach? That sound familiar to anybody? Area of a triangle is half the base times the height. It's true. Good. Here's a different version. For not just any old triangle, but what kind of a triangle have we always been playing with today? An equilateral. There's a special formula for the area of an equilateral triangle. It's this. You take the side, S, you square it, you divide it by 4, and you multiply by the square root of 3. It just rolls off the tongue. That right there is the formula for the area of any equilateral triangle where S is the side. So suppose for a second that my triangle has 9s all the way around. I want to find the area of that triangle. So we use this formula here in red. Instead of S, what do we put? Put 9. So that becomes 9 squared, divide by 4, times square root of 3. The calculator will help us with that, but plugging in isn't so bad. So we do 9 squared, divide by 4, times the square root of 3. Whatever I get, what is it? That sounds too small, no? Yeah. So the area of that triangle is about 35 units, 35 square units. So, it does work. The problem is that for the triangle, we know how long the sides are. We know they're all 9s in this example. And then if you go to the next phase, you're going to stick on a little triangle right here. How long are the sides going to be there? Yeah, what will they be if you start with a 9? They're each going to be 3, right? And so I can use my formula again, but now the sides are all 3. S is 3. The difficulty is that it's hard to find what the height is. The half base times height works for any triangle. But, you know, like in every one of these geometry problems you saw in high school, they gave you the height, or it was really easy to find the height. But in this problem, not so easy to find the height. And so it's just it's a special case. Okay, so here's the question. If we keep adding these little triangles around, just like we've been doing, what's going to happen to the area in the long term? We know we're adding space. We know the area is getting bigger and bigger. But the question we posed at the start today, does it get bigger and bigger to infinity, like the perimeter did? Or does it get bigger and bigger, but it kind of levels off and there's like some limit? You know, like maybe the area of this shape, if I do it forever, will never get more than 100. Or maybe it'll never get more than 1,000. But there's some like cap. And we had a few people who kind of felt like even though there's more triangles added all the time, that it's still like a finite amount of space in here. All right, on the next page is a table that I'm going to encourage you guys to kind of fill in. We'll fill in just the start of it right now. And I'll encourage you to fill in the rest of it later on. And then I'm just going to show you the punchline right before we end today. So thinking about the original triangle, We're starting with a side length of 9. That's just a given. And how many triangles are there originally before you draw anything new? Just the one, right? We just start with a single triangle. So there's one triangle. And then that 35.07, does that look familiar? That's the number that I just found here on the calculator, is the area of the single triangle where the sides are 9s. So we had to use that fancy formula to get the 35. Okay, so we have one single triangle. Its area is 35, so its area is 35. Not a whole lot to do there. And the area of the whole thing at the moment is just 35. But then we add some stuff. How many triangles do you add on that first stage? You add 3 little triangles. What are the side lengths? If you start with a 9, then the side lengths for all 3s. That's what you guys drew. So the side lengths are each 3 long. How many triangles did you add to the original one? You added 3. That's that guy. How are we going to find this number? Yeah, it's this fancy area formula. But instead of doing 9 squared, so it's always the side squared, how long are each of the sides in this stage? They're only 3. So the area of the little triangle that we add is going to be smaller than the 35. Turns out it's about 3.9. Is that what I wrote? Yes. So that's where that number comes from. It's plugging in that fancy s squared divided by 4 times root 3. Okay. So the question is, how much area did we add in that phase? Thinking about, I'll go back to something where we had all our nice pictures. I'm looking at this phase right here. What did we just discover is the area of a single one of these, roughly? It's 3 point, how much? 3.9? So roughly that single one that we added was 3.9, but how many of them did you add? You added 3 of them. So if I want to know how much area I added total, what should I do? Multiply. The 3 triangles that you just added. Yeah, so we're going to multiply this thing by 3 because there are 3 of them that we added. And it feels like it should be 9 point something, but it's a little bigger because of the extra stuff. So 11.7, that's the 3 little areas that we just added up all together. So I think that's written in the table here. So that's this number. And again, to find that number, we multiply these. Number of triangles times the area of each one. And now I want the area of the whole snowflake. How do I find that? We're going to add. What are we going to add? Yeah, the original triangle was 35. That was the area of the original triangle. And then we just added a total of about 11.7. And if you add them up, you get 46.8 is the total area of that star, that snowflake. And then we repeat. Just keep doing it. The good news is there's little patterns here. What happens to the side length every time? We did this already. It's a third of what it used to be. What's the new side length? If it used to be a 3, that's definitely going to be a 1. What happens to the number of triangles? So did we do that? I don't know if we counted the number of triangles. How many triangles got added in the next phase? It's 12. We've seen that number before. It used to be 12 because we thought about the 12 sides. But every side gets a triangle. So now I'm starting to feel pretty good about saying maybe, hey, this is always times 4. The 1 to 3 is a special one. Is that true? How many triangles? Oh, wait, maybe I'm wrong. How many triangles did we have? Let's look at the picture. Is it 12 or is it 9? I want to know how many triangles got added going from here to here. Okay, so I'm just going to circle the triangles that are in the new shape that weren't in the previous one. Was this guy over there? That space was already there. Was this guy over there? No, that's an extra. How about this one? That's new. How about that one? No. Okay, so then I feel like I should be skipping the ones that are on the edges. How many triangles did you guys add at that phase? There's 12 of them. 12 new triangles. Okay. So we'll say just kind of follow the pattern. Everybody here is times a 4. Everybody here is times 1/3. That new formula gives you the messy numbers. I'm just going to show you the punchline. Here it is. Make this a little bit bigger. On the first triangle, we had a 35, yes? Here's what happens to the total area. That's the column we're looking at. As we go down, you could see 46.7, that was there. 51 bigger, 54 bigger, 55 bigger, but what's happening to how much we gain? It's getting smaller. We're not gaining as much every time we step down. And in fact, if you look far enough, it seems like the numbers are hardly moving at all. And so it turns out that no matter how long you do this one, the triangle approaches something like 56.1. And here's the crazy part, and we'll end here. The final triangle, the infinite triangle, has an area that's always 1.6 times the starting triangle. The original triangle here was a 35 area. It's always 1.6 times that starting triangle, and that's it. Okay, sorry for going a little bit over today. We'll see you on Tuesday.